So, the requirement is to get the E values from the observed structure factors, the observed intensities. We take the square root of the intensity. This epsilon h, as I said, is known as the extinction factor. There is nothing to do with extinction effect, which we discussed earlier on. It is an extinction factor. For example, if we have a P2 upon C structure and we look at HOL reflections, remember that L odd reflections are all absent by systematic absences. And therefore, the weightage that is given to HOL is double the weight of a general HKL reflection. Let me repeat, a general HKL reflection, if we give a weightage of 1, that means it has whatever measurement we have is with a weight of 1. The HOL reflections, because L odd is absent and only L even present, it gets double the weight. And so, when we are dealing with HOL reflections for this E calculation, by the way, I should say that H here is a vector which refers to HKL. Okay. So, this E of H square now will have to be divided by 2 times this quantity. So, that means the division, the weightage is now reduced by half. So, you give a value of epsilon h equals 2. So, depending upon the space group and the systematic absences, you vary the value of epsilon h. And therefore, you get a normalized structure factor. This structure factor is now effectively coming from point atoms. That means atoms now are in a point and all the electron density is associated with that point. And as a result, you remember we defined the delta function earlier on. The diffraction is from a point atom, we get a delta function. So, the contribution comes from all of it will come from the point where the XYZ is located with respect to the E value. So, then what is the advantage? The advantage is now that it is not going to vary with respect to sin theta by lambda. So, the scattering angle, it is independent of the scattering angle in principle. And so, if it is independent of the scattering angle, that means there is no change in the phase that is associated with a point atom. So, it becomes very easy now to put up a logic. The logic which we have is explained in this particular diagram. This is a very crucial diagram. See, you look at 3 planes. Okay, this represents the one set of planes HKL. Let us say this is represented as H. It actually represents a HKL plane, parallel planes. You see, so the dark lines here are the parallel planes, and the dotted lines between the parallel planes represent the halfway point. That means, if this is the distance at which the Bragg's law is validated, if you now consider a cosine curve, for example, or a sine curve, the crest is at these points and the trough is at this point. Okay. So, the crest and the trough are identified as plus and minus by us in this particular table. I will come to that table in a minute. So, now we have a set of planes which are HKL. And you see that in this HKL plane there are 4 regions of high electron density. That means atoms are contained in these 4 regions A, B, C and D. So, these 4 regions contain atoms. That means the value which you get for the structure factor and therefore the E of H will be very large. So, these we are now dealing with the highest possible E values. So, after we get the E values, we arrange them in the order of the value. So, the highest value is put on top, the next highest next and so on. So, once we order that, we have to take the highest possible E values and take 3 planes. One plane is now this represented by H, the other plane is represented by K, which is now this the origin. So, we have a K here and a K there, and similarly the half points are denoted by dotted lines. That means they are now the troughs of the wave. So, if you have a wave, let me make it clear because that is an important thing to happen to observe. So, if you now take a wave which is like this. Okay. So, this to this is now the wavelength, right. One single wavelength is the point here to that point, or is it the point from here to that point. In fact, that is correct. The point, this point to that point is the wavelength. So, if this is the wavelength, then you see that this is represented by solid lines, and this is represented by dotted lines. So the solid lines will now correspond to one single lambda. So 2d sin theta lambda will be satisfied, and so we will have these coming in the crests of the wave, and this comes in the trough of the wave. So the alternates, so if you have a HKL plane which is shown here, let me go back there. If you have a HKL plane which is now going here with respect to this origin, 1 unit away, this is the next one which is going here. Between them there is a set of dotted lines which essentially represent the trough of that particular wave, which is associated with the plane H, which could be H1 K1 L1. We call it as H, let it be H1 K1 L1. Similarly, this is the value of K, which is now represented perpendicular to that direction. So let's say this, and that, and then the alternate dotted lines are indicated. And we take the third set of planes H minus K, which is in the direction of the diagonals. So we essentially represent all three directions here. So if the logic is the following, you consider three very strong E values, HKL values, which are intersecting with each other to represent this plane, and they are intersecting in such a way that they pass through electron density positions A, B, C, and D. Now what happens when it passes through A? When it passes through A, the value of H, as we see here, is a full line. That means it is positive. The value of K is positive down here, and the value of H minus K is also positive. So the three values now which intersect at A will give rise to plus, plus, plus. So that means if you are looking at a centrosymmetric structure, these three now represent a value equal to 0, the phase value equals 0. So this is sin of H, sin of K, sin of SH minus K. Now the product of these three, SH, SK, SH plus K, will therefore become positive. This is what is important. When we have three very strongly the diffracting planes which pass through either at the trough or at the crest through these points A, B, C, and D, where there is electron density. That means atoms are located at these positions. Then you will have the product of SH, SK, HK, and SH minus K always positive. And one can associate a probability with this, and that is how direct methods are carried out. So we now therefore take three strong highest E values. These E values are defined in such a way that we have 4 points A, B, C, D, which are electron density rich, and these three planes intersect such that they pass through these electron dense regions. So whenever they pass through the crest, we call them positive, and whenever they pass through the dotted lines or the troughs, we call it negative. So the B position you see is, except for the H, which is now this way, this is the H value, except for H, which is positive at B, these two are going to be negative, but the product is still positive. Similarly, in the case of C, you see that the value of L is positive, the other H and K are negative, and so the product is still positive. The point D, you have again one of them positive, which is the K value, which is positive here, and these two are going to be negative. So essentially, if you look at this diagram, you have possible combinations with individual signs associated with these planes. It hardly matters because there is rich electron density associated with these three planes, and that electron density therefore gives, for all 4 positions where there are atoms, the product of the signs is positive. So that would mean that wherever there is an atom, if you take intersecting planes, those intersecting planes should be having a positive value. And this is the logic with which direct methods work, because as you go to lower and lower E values, the reliability with which you can assuredly say that these three products are positive becomes less and less. So you can calculate a certain probability that is associated with it. We do not go into the detail of this discussion because this is not in the purview of our current course. This needs an advanced crystallography course, but I will tell you how we normally do the direct methods. So the direct methods now calculate normalized structure factor amplitudes, set up these phase relationships. So I showed it in terms of signs, but they can have different values of phi depending on whether it is a centrosymmetric or a non-centrosymmetric structure. So instead of sign, you replace it by the phase. So the phase of H is nearly equal to the phase associated with H minus k plus the phase associated with k. So this is the relationship which we are going to use, and find the reflections to be used for phase determination. Based on this, you generate phases for, let us say, something like 100 reflections. You don't have to generate phases for all the reflections. The top E values are taken, top 200 E values, and within that 100 E values, any combinations of this kind which we can develop, we can now associate this equation with them and find the reflections to be used for phase determination. And then you assign starting phases to these. If you assign positive sign for everything in a centrosymmetric case, you will get nothing. You will get a very strong peak at the origin, because all phases cannot be all positive. Some of them must be positive, some of them should be negative, like the way we indicated in this diagram, in the previous diagram. So based on this logic, we calculate now what is the probability that this product is plus. So in this example where I have shown, the probability is 1.0. But we can calculate the probability as we go down in the E values. The probability value keeps on going lower and lower. The confidence level with which we can assign these values become lower and lower. That means the confidence with which we can assign phases for reflections become lower and lower. But then we can put a cutoff on the probability limit. Let us say we cut it off at a value of 0.9. Then we will get the solution for the phases for the first 10 top E values. That may not be sufficient. What we want is a reasonable number of reflections based on which we can calculate a Fourier map, which is called the E map. And that Fourier map will give us the approximate positions of the atoms. It will give us the trial structure. So there is no involvement of whether the atom should be heavy or light. It does not matter now, because it is independent of the Z value, because we have taken this in the denominator. We have normalized the structure factors. Since we have normalized the structure factors, there is no dependence upon the nature of the atom. It is only dependent upon where the point atoms are situated. And as a consequence, this probability development of phases will depend upon how many starting phases we can have. So at this stage, there are different ways in which one can do it. There is what is known as a symbolic addition method. There is what is known as a phase development method and phase criterion development method, and so on. So an estimate of each phase determined is given by this expression. So this expression depends upon how strong these three reflections are and what is the total number of atoms in the structure. So we assign starting phases to a few reflections. For those reflections which we do not know the phases, we can either give symbols, which is known as the symbolic addition method, and try to solve the sign of the symbol if it is a centrosymmetric structure. Or you take about 20 such reflections, strong reflections, give random phases to them. So use a random number generator and assign phases to them. Compute the E value. That will be wrong anyway. You won't get any. Compute the E map, it will be a junk. So then what you do is you allow this to refine, and you find the newer phases, making use of the fact that we should always have this reliability on the strength of the E value. The stronger the E value, the better is the phase determined. So keeping that in mind, we can do an E map calculation based on the phases. We give random phases to about 20 of them. Keep changing the phases using a random number generator. Every time calculate the E maps. So thousands of E maps can be calculated. Eventually we will hit a combination which is closest to the final structure. Then the E map will give you the required atom positions. So this is why this method is called direct methods, because it can be directly calculated, the phases. And so we have therefore the structure information. The ease with which programming can be done using random number generators and so on is mathematically very simple, and therefore the computer programs which are available are extraordinarily fast. The computation is also fast because we use what is known as a fast Fourier algorithm, FFT, fast Fourier transform, and that FFT will make sure that your E maps are computed at very quick time. So once you have that, you calculate and interpret the electron density map, which is referred to as the E map. You will get the trial structure. I do not think beyond this we should worry about the phase determination protocols, because that would make it an advanced crystallography course, which we are not now really interested in. What we are interested in is the symmetry. Now, where does the symmetry come into the picture here? The symmetry came automatically into the picture. It came automatically into the picture because we are talking about the electron density and the associated phases with the planes which are strong. A strongly reflecting plane, therefore, in principle should have electron density content in it, or the contributions of various atoms to that particular plane should be very positively significant. If that has to be significant, then the nature of the atoms that are arranged inside this particular space group should be related by a proper symmetry relationship. So, symmetry again now controls the way in which this propagation of the phases occur, and therefore, again we have to see that our requirement of symmetry and in the structure is very crucial. That is all I can tell about the methodologies in this particular course, because it otherwise becomes out of scope. We now change gears. We now change gears and go to a new area, and this is an area where many of you are interested, because it is not always possible to grow good quality single crystals. In many cases, there are reasons why good quality single crystals will not grow at all. However, it is possible to get polycrystalline phases. So, polycrystalline growth is quite possible. That means the size of the crystals, or the crystallites as we call them, are so small that each one is a single crystal, but then they come in the form of a powder. We can't look under the microscope and separate one single particle. These particles are of course crystals. So, a large number of crystals now are assimilated in the form of a powder. So, if we get a powder sample, particularly an organic chemist synthesizes and gets a solid form of in the form of a powder, the first check he will do is to put it with XRD. The reason why it is done is that if it gives a sharp set of reflections like this, then it is a polycrystalline sample. It is possible that we do not get this kind of a sharp diffraction line when we do the X-ray measurement. We may get a large hump like this. Then the conclusion is that it is an amorphous material. So, it is possible to have amorphous materials also looking very shiny, like for example glass. Glass is not a crystalline material, it is an amorphous solid. So, essentially what we therefore do is, in a 3-dimensional single crystal which we discussed so far, we have isolated HKL positions, but all these HKL information is contained in this 1-dimensional profile. So, you have a 3-dimensional reciprocal lattice which we have discussed so far. The 3-dimensional reciprocal lattice gets condensed into a 1-dimensional profile like this. Whatever is the information here is also contained here, but there is a severe overlap of these reflections, because we are now plotting intensity versus 2 theta. This 2 theta is the scattering angle, and as we go from 0 to let us say 90 degrees or 100 degrees, the reflections which dominate are appearing here. It may so happen that under every peak there may be several reflections, we do not know, but a typical XRD pattern with a good polycrystalline material will look like this. Now, how do we use this information to get to the structure? This is something which is very crucial for pharma industries particularly, because very often the growth of a good quality single crystal is a issue. In many other cases also, when materials are made and synthesized, normally polycrystalline forms are available very quickly, but growing a single crystal of the material is an issue, which is a problem in organic, inorganic or any other area of solid state chemistry. So, we did discuss how we grow the crystals in the last couple of classes, but then even with we make all these attempts, it may so happen that we may not get good quality single crystals. So, we have to deal with polycrystalline samples. So, if we have polycrystalline samples, how do we get to the structure? That is the next issue which we will take up. So, there are a certain set of cautionary points one has to take, which nobody takes when we do the powder diffraction. See, in case of a single crystal, you do not have to take any cautionary steps. This is another big advantage. If you get a good single crystal, you look at through the microscope and the microscope shows the extinction effect. Then you assume that the crystal is good, put it on the diffractometer, it will give you the diffraction spots. And if the spots are good and you have enough information on the reciprocal space, you now know how to go to the structure determination and also final refinement and so on, which we have briefly looked into. So, we know the structure determination protocol for a single crystal. What happens in the case of a powder? We can just not take a powder and throw it on the diffractometer, which most people do, and you put it on the glass plate or whatever is the plate given by the company manufacturer, and put the sample and then collect the data, and then you will see a picture. And that picture, if it is sharp enough peaks, you say, oh, I have a polycrystalline sample. And very often in industry what they do is to look at the diffraction pattern, and then if they know roughly what the material is all about, they get the diffraction pattern already there available in the databases, and then put one on top of each other and compare the peaks and say, oh, we have made the same compound. These are all more or less criminal acts as far as diffraction is concerned, because X-ray diffraction needs a little more, it has a little more honor than what people give. So, it gives us more information than what is required. As I already said, powder diffraction has all the information of the three-dimensional reciprocal lattice imaging, and therefore, we should in principle be able to use powder diffraction even for structure determination. It is not just that we compare two samples and say, oh, they are one and the same, and or if we get a slight differences in the peak positions, we cannot say we have made a polymorph or we have made a new compound and whatever. So, those conclusions which are done sometimes in industry have landed them in serious trouble, and it should not be done. So, what do? We first have to worry about how we prepare the sample for the diffraction experiment, and of course, then we have to worry about what is the wavelength which we are going to use. Sample preparation, it is generally recommended that even though we get the experiment to give us a powder, it is better that we make sure that the powder is nicely prepared. By prepared I mean we take the sample in a pestle and mortar and we grind the sample. After grinding the sample, in principle nobody seriously does it, but in principle we have to pass it through a sieve which has a certain dimension. So, let us say we pass it through a sieve which has 100 microns, and it is like getting the atta prepared for your chapatis. So, you just play with the sieve and then get the powder of 100 micron sizes only assimilated in one place, and take that as the sample, and then you prepare the sample by the method which you are going to use. There are three different ways in which you can collect powder data. This is something which probably is not very well described everywhere. The routine X-ray diffraction equipment which we get for powder diffraction is the reflection mode. You will have the sample on a horizontal glass plate, you spread the sample on top of it, then X-ray will come from here and then fall on the sample, and the Bragg diffraction is satisfied. So, it will go at an angle satisfying the 2d sin theta and lambda, and you will get the reflection. And you may put a counter or a measuring device there, the detector, and the detector will catch the intensity that is coming out. And then you move the 2 theta circle so that the detector moves with it and collects with respect to 2 theta the data. So, we get intensity versus 2 theta. That is the usual geometry we have in many of the standard setups. One can also collect the data with what is known as the transmission mode, where the equipment is such that we now allow the X-rays to pass through the sample. The sample now can be rotated as well, and as the sample rotates, the X-rays pass through it, and then they come out, the diffraction is measured in 2 theta with respect to the detector. So, this is a flat horizontal goniometer system where you have the goniometer put in a direction of the incoming radiation, and that will now carry a container in which we have the sample. So, the sample is now exposed to the X-rays in a perpendicular manner. It is no longer the reflection geometry, it is called the transmission geometry. The age-old method of the powder diffraction which was discovered and used in the earlier days was to take the powder and fill it up in a capillary tube. These capillaries are very special, and these capillaries have a property that they are not absorbing the X radiation. They indeed scatter the radiation very little other than the scattering that is coming from the sample. So, we have to now have the sample fully filled inside the capillary, and now the capillary is rotated, and this is known as the Debye-Scharer mode due to the two people who found this methodology. So, we have a capillary, the capillary rotates in a direction perpendicular to the X-ray beam, and we measure the diffraction coming out, and that will be the 2 theta circle. So, in all these cases the data recorded is intensity versus 2 theta. So, suppose we have a compound, this is the example of a compound, you may not be able to see it. So, I will read it out. This is the sample which is I will write it down what the sample is. The sample is mica. So, you have all seen mica sheets, they are all layered, and they are layered on top of each other. So, for the reflection geometry, what you can do is take a sheet out, put it on your standard diffractometer setup, and then do the reflection mode. When you do that, you will get a pattern like the one shown on the top. This is the pattern you will get. So, you are going to get effectively 1, 2, 3, 4, 5, 6, 7 peaks. The XRD is of course 0 to 60 degrees, which is shown here, but you will get this the 80 degrees, sorry, 0 to 80 is shown here. So, you will get peaks corresponding to these HKL positions. You can find out the HKL positions because 2 theta you get the D values. From D you can find out what are those HKL values. Once you know the ABC alpha beta gamma, you know that methodology. If you do the transmission mode, you will get a different pattern altogether. It is the same mica, but your XRD pattern is different now. Now, this is something which is to be explored very carefully. The reason is that the atoms in mica are all in a given plane, and so the scattering is dominated by that particular plane. So, you get very strong reflections of the planes here, and in the case of a transmission mode, that plane may be associated with this, where you see no diffraction coming. In the reflection mode you get a diffraction which is very strong here. So, this tells us that these two methods are now indicating the mica to be two different compounds altogether, but it is not the case. This kind of a thing happens in many layered compounds. There are a lot of people who work on layered inorganic materials, organic inorganic layers, they are parallelly packed them, the hybrid structures. In all those situations, these two methods are not the recommended methods for data collection. The recommended method is the Debye-Scharer approach, the capillary method, where you rotate the sample. So, the crystallites inside the capillary, they orient themselves in all possible directions. So, X-rays now fall on those crystallites in different directions. So, you get diffraction from all different orientations. So, you see a very complicated pattern for mica here, but what you see for these two modes is very different from each other, and therefore, when we are dealing with layered compounds, one has to be extraordinarily careful. So, the method that is generally suggested to be used is the Debye-Scharer mode. In fact, Debye-Scharer mode is the best mode of data collection for any powder data. But this is not the case with all molecules and all structures. So, it is okay when we get a XRD to be taken, we use the reflection geometry. So, reflection geometry is the preferred mode of data collection because it is cheap. Most of the commercially available instruments are using the reflection mode geometry. The entry in the database for mica is given below, and you see that for every point here there is a corresponding HKL. So, this is the calculated pattern for mica. So, you can solve the structure of mica by growing a single crystal of mica and then determine the possible HKL positions, and those HKL positions are shown as lines here, and this is therefore the simulated XRD pattern, and this is available in the database. So, you see there is a one-to-one correspondence between this and that, showing that all the peaks that are coming in the case of capillary are not impurity peaks. They are all coming due to the presence of peaks which are in the structure of mica. But those now do not appear because of the fact that mica has the orientation effect. This particular thing is known as the orientation effect, this phenomena, which we described in case of the reflection mode as well as the transmission mode. The highest peaks of these are coming due to the exposure of that particular plane from which the diffraction is coming, and only that dominates, because we are not either, in this particular case of reflection mode, we are not rotating the sample either, and so it is coming from one particular position. So all these therefore tell us that the mode of data collection is something which is very important to be remembered, particularly when we are dealing with layered compounds. Now, what is the quality and quantity of data one would like to have? If you want to determine a structure, you should get as many data points as possible. The same logic as in case of single crystal analysis, where we had to use as many data points as possible. That means the maximum extent of data which we can acquire in the 2 theta range. So suppose let us say we go in the range of 1 to 100. If we go in the range of 0.02 degrees in 2 theta, we get nearly 5000 data points. So we should measure every data point in a powder pattern. So we call it, oh, this is in the background, this is in the peak and all that. It is our decision. But basically we are measuring the intensity which is along the x-axis, y-axis here at every point along 0.02 degrees in 2 theta. If we go to synchrotron radiation, we can measure it at 0.005 degrees in 2 theta. So you get something like 20,000 data points. So one would say, why we do this routine XRD? Let us go to synchrotron radiation. So if you are determining the structure of sodium chloride, why go to synchrotron radiation? So you don't need a missile to kill a sparrow, right? In Kannada we say Gubbi Mel Brahmastra. So we don't have to go to find the structure of smaller molecules, smaller compounds to actually go to synchrotron radiation. Synchrotron radiation becomes a requirement when there are some special issues concerned with small molecules. What about protein structures? So in case of protein structures, we need large number of data points. So suppose we want to determine the structure of a protein somehow by the powder diffraction method, which is nowadays a possibility, even though there are not many structures which have been determined. People have done the powder diffraction pattern of structures which are known and tried to fit the parameters associated with the structure to the observed diffraction pattern. There we can definitely use synchrotron radiation because we need lot more data points. So the requirement of the data points is one issue. The second issue is, of course, lies with the accuracy with which we measure. So since we now have a sample properly prepared, we have a proper lambda used, so we can change the lambda. We don't have to use copper K alpha as is believed everywhere to be the mode of data collection. We can use molybdenum, we can use silver radiation. So the more lower is the lambda value, we know already about resolution, we get better resolution. So use of silver radiation, for example, will give us much better resolution than use of copper K alpha radiation. You remember that formula where we calculated the number of possible reflections from a single crystal diffraction. We saw that in case of copper K alpha we had 14,700. In case of molybdenum we had 1,42,000 reflections. Silver radiation will probably give us more than 2 lakhs of reflections. So we can always use the right source for the right analysis. So it is not always necessary to go to synchrotron radiation for powder work. If you are doing some other special observations with respect to, let us say, non-ambient work, high temperature, low temperature powder diffraction, or for that matter we are looking at an in situ reaction process which is occurring in a powder, photochemical reaction and so on, then going to synchrotron radiation would be of enormous use. So synchrotron radiation of course can be used for powder data as well. That is in a nutshell the gist of the whole story. So what do we do first further with the powder data? So if most of us do the powder data collection like this, and if you go to pharmaceutical industry or for that matter any materials scientist, they want the following information. They want the structure information if possible. They want to know the crystallinity, the extent of crystallinity. This particularly so in case of pharmaceuticals. They want the phase purity, which is very important. They want the crystallite size, And of course, the instrumentation characteristics become very crucial for aligning all these things. The positions of the peaks and intensities are very crucial. So, we have the x axis giving us the geometry, the y axis giving us the structure information. So, the x axis is the one which is most crucial for most of the industries, because they want to get to the cell dimensions and the possible crystal structure information that can be derived from this. Other than that, in pharmaceutical industry, they want to distinguish find out the API, the structure of the as prepared ingredient and pharmaceutical ingredient, excipients if any, other required materials for tablets, capsules and so on. And they also want to quantify in case of aerosols. And then of course, the major thing lies in terms of polymorphs and co-crystallization. Co-crystallization can give rise to solid solutions, it can give rise to co-crystals, it can give rise to eutectic phases and so on. So, all these issues come up and the answer comes from powder X-ray diffraction, believe it or not. And so, powder XRD therefore is a very, very powerful tool. As I already mentioned earlier in some context, that the cell dimension you determine from powder diffraction is much more accurate than the cell dimensions you get from the single crystal measurements. That is because a powder sample has a large number of crystallites, many thousands of crystals, whereas a single crystal has only one crystal. So, that therefore allows for averaging effect, and therefore you get very accurate cell dimensions, and therefore the determination of space groups and other things become fairly straightforward in that context. Let us take the case of a standard sample. Most of the materials, most of the manufacturers give us this particular compound LAB6, and if you record with copper K alpha, you get a pattern like this, a very beautiful pattern, and you go from 20 degrees in this case to 140 degrees nearly, and you get a beautiful pattern. By beautiful I mean you see the background. The background is steady throughout, so there is no deviation in the background, and you get peaks which are fairly sharp. If you look closely, they have a certain width associated with them. I don't have time to discuss in this course what is the reason for the width and so on. That is again a very advanced course in powder diffractometry. However, we see that these are the peaks. So, if the compound now belongs to a cubic, we discussed this already in case of single crystals. We found out how the d square HKL values can be determined in case we have the information on the HKL as well as the cell dimension. The cell dimensions can be determined once we have HKL and D of HKL available to us, and it varies from various systems, cubics, tetragonal, hexagonal and orthorhombic and so on. Most of these indexing is done through automatic programs which are available in free domain space. There is a program called TRIAR, there is a program called DICWAL, there is a package called CrisFire, but I am told by some of my students that CrisFire is no longer active. Obviously, because of the fact that CrisFire probably was on a previous generation computing system, and now the computers have changed their architecture. So, nobody did make an attempt to write that program fresh possibly. But there is this YANA package, which is again a free downloadable package, which does everything. It does single crystal refinements, it does standard powder diffraction analysis. It also does the so-called Rietveld method, which we will briefly touch upon as we go along further. So, how do we index these spots? So, now you see here is a pattern. Okay, there you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. So many peaks. Okay. So, I will take the first 12 peaks associated with this, and these first 12 peaks I will start giving the least possible HKL values. That means I will start with 100, then the second one is 110, third one is 111. This is a cubic system. See, in a cubic system what you have is this expression h square plus k square plus l square is equal to half to the power half, right. So, what are the HKL values we can think of? We can think of the HKL values to be h equals 1, 0, 0, and in a cubic system 1, 0, 0 is same as 0, 1, 0, is same as 0, 0, 1. So, we do not need to consider those. and that is why the next one we consider is H equals 1, K equals 1. So, that is why it becomes 1 1 0. Then of course 1 1 1, we go to 2 0 0, 2 1 0, 2 1 1. Then 2 2 0, 3 0 0, 3 1 0, 3 1 1, 2 2 2 in a cubic system. So, these now will h square plus k square plus L square is equal to 1 in this case. H square plus k square plus L square is equal to 2 in this case. So, you give these numbers 1 2 3 4 5. When you come to number 7, you can't have a combination of HKL which is integer, and it will generate the number 7. So, we will not have 7. In other words, h square plus k square plus L square equals 7 is not possible. Check it out. So, give different values of h, different values of k, different values of L, you will not get to 7. So, we have to leave it out, and then rest is 2 2 0, 3 0 0, 3 1 0, etc. So, this is the process of indexing. So, if you have a cubic system, a simple cubic system, and you have the formula h square plus k square plus L square, and you are dividing this by a square to get to the value of d of HKL. What you get from this is the I versus 2 theta. From 2 theta you calculate sin theta, and then 2d sin theta and lambda will give you the d values. Those d values now you associate with these planes. The very highest index could be 1 0 0, the next one is 1 0 0, 1 1 0, and so on. So, when you give these values, these will now start to fit with each other if this is a cubic system. If it is not a cubic system, you will not get integral fits of this kind. Then you have to think that this system does not belong to a cubic system. So, the process of indexing therefore is all automatized. So, we are not in a position to go to the discussion of how we index it. So, we have to go to these program packages which will do these indexing whatever be the crystal system. So, what I will do is instead of going into the detail of powder diffraction, I will discuss the powder diffraction uses relevant in pharmaceutical industry. This is also we can generalize it in chemistry, for example.